Welcome to the deep dive. Today, we are plunging into a really interesting preprint paper. It introduces something called flash normalization, or FlashNorm for short.
Right.
And the big idea here is finding a faster way to handle these normalization layers. You know, the ones that are just absolutely fundamental inside large language models.
Mm-hmm. Core components.
We've got this paper as our main source, and, well, our mission for this deep dive is to really unpack FlashNorm. How does it actually work? What makes it faster? And maybe what does it mean for LLM design going forward?
Yeah, and it's definitely worth saying upfront just how critical normalization is. RMS norm specifically, root mean square normalization, that's a key piece. And like so many big models people know, Llama, Mistral, OpenLM.
Right, big names.
Exactly.
Yeah.
So any speed up here, even if it seems small, it's not just some minor tweak. It affects a really significant part of the modern LLM landscape.
Okay, let's maybe take a step back first. Before we even get into FlashNorm, why do we have these normalization layers in neural networks in the first place? What's their job?
That's a great place to start. Generally speaking, they're super important for just making training work reliably. Stability, performance.
Okay.
They help keep the numbers, the values flowing through the network under control. Without them, you can get these exploding gradients where numbers get huge, or vanishing gradients where they get tiny.
Makes training impossible, basically.
Pretty much, yeah, really difficult. So normalization helps prevent that.
And RMS norms specifically. How does that one work?
Right. So RMS norm, which is kind of the baseline for this paper's idea, its job is to take a vector, let's say the output from the layer before it, and scale it. And it does this by dividing every single element in that vector by the vector's root mean square value, the RMS.
Root mean square.
Yeah, think of it like a measure of the vector's overall size or magnitude. The calculation is actually pretty straightforward. You square all the numbers in the vector, find the average of those squares, and then just take the square root of that average.
Square mean root. Got it.
That's your RMS value. And you use 1 over that value, the reciprocal, to scale the whole vector.
Okay, so vector comes in, calculate its RMS, scale the vector.
Yeah.
Simple enough. And the paper points out that usually right after this RMS norm step, there's a linear layer, like a matrix multiplication.
Exactly. That's the really common pattern. Data gets normalized, then it immediately goes through a linear transformation. That specific sequence, RMS norm followed by linear, that's the target for FlashNorm.
Right. So FlashNorm, they claim it's exact mathematically the same result, but faster. How? What are the tricks?
Okay, so FlashNorm uses 2 main ideas, 2 key optimizations. The first one is something they call weightless normalization, or sometimes merging the weights.
Merging weights.
Yeah. See, normalization layers often have these little learnable parameters, scaling weights, usually called gamma or just G. They're multiplied element-wise after the main normalization happens.
Okay.
What FlashNorm does, or the first part of it, is it shows you can take the scaling weights, the G values, and instead of having them as a separate step, you can mathematically merge them right into the weight matrix of the linear layer that comes next.
Oh, interesting. So you just like tweak the matrix of the next layer so it includes the effect of those normalization weights.
Precisely. You calculate a new, slightly different weight matrix for that linear layer, and the benefit is immediate. Right. You've just eliminated a whole separate tensor of parameters, the G weights, and the computation step that applies them.
Fewer things to store, fewer things to compute.
Exactly. It simplifies the model structure. And they note this works fine whether that next linear layer has its own bias term or not.
Okay, that's clever. Bake the normalization weights into the next layer. What's the second big idea? This sounds like where the flash part might come in.
Yeah, this one's, I think, the really core insight. It's called deferred normalization.
Deferred. Okay.
So instead of normalizing before the linear layer, like we just described, FlashNorm says, hold on, let's swap the order. Do the linear layer calculation first, the big matrix multiply, and then apply the normalization scaling factor, the 1 RMS part, after that.
Wait, hang on. You can just flip them. How does that work?
Yeah.
Doesn't multiplying by a matrix and then scaling give a different result than scaling and then multiplying by the matrix?
Well, this is where a key mathematical property comes in, and it relies on something pretty common in models like Llama or Mistral. The linear layer in the sequence often doesn't have a bias term.
Okay, bias-free linear layers.
Right. And because matrix multiplication distributes over scalar multiplication, basically, WSA is the same as SWA, where W is the matrix, S is the scalar, and A is the vector.
Oh, okay. I see. You could pull the scalar S, which is our 1 RMS factor, outside the matrix multiplication.
Exactly. You can move that scaling factor from before the linear layer to after it, and mathematically the end result is identical.
Wow, okay.
And the paper makes this nice analogy to flash attention, which does something similar, right? It defers the scaling by the softmax denominator.
Right, so why do this? What's the benefit of deferring the scaling?
The big win is how it changes the flow of computation, especially on parallel hardware like GPUs.
Okay.
Think about the standard way. Calculate RMS, scale the vector, then start the big matrix multiplication for the linear layer. The matrix multiply has to wait.
Yeah, dependency. Linear layers blocked until normalization finishes.
Exactly. With deferred normalization, you calculate the original vector's RMS value at the same time as you start feeding that original vector into the linear layer's matrix multiplication.
They happen in parallel.
Precisely. The RMS calculation, which might happen on, say, a vector processing unit on the chip, runs concurrently with the matrix multiplication on the matrix unit. You remove that waiting time, that serial dependency.
That makes a lot of sense, especially for speeding things up.
Yeah, it removes the bottleneck. And this ties into other research they mention, how sometimes just the way normalization is implemented can slow things down because you need separate compute steps or kernels on the GPU. FlashNorm's approach naturally reduces the number of these separate steps.
Okay, so FlashNorm starts with RMS norm as the base case. Can these ideas, merging weights, deferring normalization, work for other kinds, like layer normalization or this dynamic tan DYT thing? They sometimes have extra bits, right, like bias terms.
Yeah, good question. The paper shows how you can extend these ideas. So layer norm or DYT sometimes add a bias vector after the scaling step.
Right.
What they show is you can take that bias vector, the normalization's bias, and effectively push it past the linear layer. You combine it with the linear layer's own bias term if it has one.
So you just add the two biases together at the end.
Basically, yeah. You create a new single bias term for the output of the linear layer that incorporates both. This gets rid of that separate normalization bias vector. And once that's out of the way, you can then merge the normalization scaling weights into the linear layer's matrix, just like we talked about before with RMS norm.
Okay, clever. Handles the bias.
Oh.
But what about the other big difference with layer norm? The mean centering. Layer norm subtracts the mean before it scales by the standard deviation or RMS-like value.
Right, the centering step. That's another really neat trick they describe. If your layer norm with its mean centering comes after a linear layer,
Okay.
you can often eliminate the entire mean centering calculation.
Eliminate it. How?
Well, the idea is you can mathematically express the mean calculation, which normally uses the output of that preceding linear layer in terms of the input to that linear layer and its weights. By rearranging the math, they show that the final mean-centered output can actually be calculated by just using a different linear layer one with slightly modified weights acting on the original input.
Whoa. So the effect of subtracting the mean just gets absorbed into the weights of the linear layer before it.
Exactly. The matrix multiplication itself is adjusted to produce the already mean-centered result. No need for a separate step to compute the mean and subtract it.
And the practical implication of that is?
This is potentially huge. It means you could take an existing model trained with layer norm, and just by modifying the weights of the linear layers involved, you could make it behave as if it were using RMS norm without the mean centering. You might get some of the simplicity or efficiency benefits without having to retrain the whole massive model from scratch.
Wow, retrofitting existing models. That's really powerful. Okay, so we've got these core ideas. How do they actually play out in specific parts of an LLM, like the feed-forward networks, the FFNs, or attention?
Good examples.
Yeah.
Let's look at FFNs first. They usually have, two linear layers with an activation function sandwiched between them. The first linear layer often expands the hidden dimension, so you can apply FlashNorm there. If the FFN uses ReLU activation, which is super common, ReLU has this nice property. Applying ReLU to a scaled input, ReLUA, is the same as scaling the output of ReLU, assuming the scale factor S is positive.
Scale invariance.
Exactly. So you can take that normalization scaling factor, the 1 RMS that would normally happen before the first FFN linear layer, move it through that linear layer, through the ReLU, and only apply it much later, maybe even at the final output of that FFN block. It saves doing the scaling multiplication inside the block.
Neat. Pushing the scaling all the way out. What about those GLU variants? They're popular too.
Similar idea applies. GLU, GGLU, SWIGLU. They're a bit more complex, often with two parallel linear layers whose outputs get multiplied together. But again, you can usually identify one of the normalization scaling factors and defer it, push it towards the end of the FFN computation, saving some operations.
Okay, still deferring where possible.
Yeah. And there's even a special case for things like re-GLU or bilinear GLU, where you can sometimes eliminate both the scaling before the activation and combine it with the scaling at the output. They note an interesting detail there. The final scaling factor becomes the reciprocal of the mean square, which is like 1 RMS squared.
Huh. Interesting twist. Okay, that's FFSIs. What about attention? Especially with rotary position embeddings, which seems to be everywhere now.
Right, attention is crucial. So FlashNorm applies very nicely to the linear layers that generate the query Q and key K vectors.
Oh.
You can merge the normalization weights into those Q and K linear layers, just like we discussed.
Okay, standard weight merging.
Then for rope-E, there's a specific optimization. Rope-E works by rotating parts of the Q and K vectors using sines and cosines based on position. That scaling factor, the 1 RMS from the normalization that you normally apply to Q and K before rope, you can actually fuse it, multiply it directly into rope-E sine and cosine vectors before rope-E is even applied.
Oh, so the rope vectors themselves get prescaled.
Exactly, and that's efficient because those sine and cosine vectors are often shared across all the attention heads in a layer.
Right. Compute them once, prescale them, then share. Saves work.
Precisely. Saves a bunch of multiplications across all heads. And they also mention that the one-headem scaling factor from the standard scaled dot product attention can often get fused in there as well.
Bundling all the scalars together.
Pretty much. The one catch they mention is for the value v vectors linear layer. That one doesn't usually go through rope-E, so its normalization scaling still needs to happen at its output.
Got it. So Q and K get the rope-E fusion trick. V gets standard deferred scaling.
Basically, yes.
Now, the paper also dives into something called QK normalization, which is apparently used in models like OpenLM. And they say FlashNorm's deferred scaling doesn't directly apply there for Q and K, but they still found ways to optimize.
That's right. Even when you can't do the full deferred normalization swap for Q and K, like in this QK norm setup, they found a couple useful tricks. First, they found a way to eliminate one of the RMS calculations. If you have a linear layer that already has normalization weights merged into it, like from FlashNorm applied earlier, and then it's followed by another normalization step, like this QK norm, the scaling effect from the first step can partially cancel out with the scaling calculation in the second step. Because RMS is scale invariant, RMSA is SRMSA.
So the scaling factors interact, and you can skip computing one of the RMS values.
Essentially, yes. You avoid a redundant RMS calculation because the scaling effects sort of counteract each other mathematically.
Okay, saves an RMS calculation. What was the second trick for QK norm?
The second one is, again, about fusing weights with rope, but this time it's the QK normalization's own scaling weights. If those weights are shared across attention heads, which they are in OpenLM, you can multiply those shared normalization weights into the rope-E sine and cosine vectors. Very similar to the earlier row trick, you create pre-scaled, fused rope-E vectors that incorporate the normalization weights and share those across all the heads. Saves operations again. Needs a bit of weight rearranging, they note, but same principle.
Okay, so even when the main FlashNorm trick doesn't fit perfectly, they're still hunting for ways to merge, fuse, or eliminate steps, especially leveraging rope-E and shared weights.
Exactly. It's all about that mathematical reorganization to cut down on the actual work the hardware needs to do.
And they really focus on this idea of RMS normalization being a bottleneck, right?
Yeah.
Especially you mentioned batch size 1, like when you're just running inference, getting one answer for one prompt.
Yeah, exactly. They use this simplified picture of a processor. Imagine one part that's good at vector stuff, calculating RMS scaling vectors, and another part that's the powerhouse for matrix math, the big linear layers.
Vector unit and matrix unit. Okay.
In the standard setup, without deferred normalization, the matrix unit is often just waiting. It has to wait for the vector unit to finish the RMS calc and the scaling before it can start the matrix multiply.
The dependency we talked about.
Right. FlashNorm, with deferred normalization, breaks that dependency. The matrix unit can start crunching the linear layer at the same time the vector unit is calculating the RMS value from the original input.
Parallel execution.
Exactly. They run side by side, no more waiting. The final scaling step at the end might even overlap with the start of the next operation. It just smooths out the pipeline and removes that idle time.
So theory sounds good. Parallel execution makes sense.
Yeah.
Did they actually measure the speed up? What were the results?
They did. They reported some experiments on an OpenLM model, the 270 million parameter one, running with 4-bit quantization on an M1 MacBook Air.
Okay, specific setup.
Yeah. And they saw inference speed go from about 204 tokens per second to 225 tokens per second.
So roughly a 10% speed up.
Around that, yeah, for that specific model on that hardware, which, it's a speed up, but maybe not a game-changing leap across the board.
Right, 10% is nice, but maybe not earth-shattering given
Yeah.
all the complexity we just discussed.
Yeah.
So if the speed up is, let's say, modest in some cases, what's the bigger picture here? What's the main takeaway?
I think the paper makes this point quite well. It's not just about the raw speed up percentage in one benchmark, it's also about the simplification.
Ah, yeah.
Think about why people moved from layer norm to RMS norm in the first place. It was simpler, fewer computations. Or why some models got rid of bias terms. FlashNorm continues that trend. Merging weights reduces parameters. Reordering operations can lead to fewer distinct kernel launches on the GPU.
So it cleans up the computational graph, makes it architecturally simpler.
Exactly. It offers a potentially cleaner, more streamlined way to implement this very common normalization than linear pattern. That architectural simplicity is valuable in itself for implementation, for potential future hardware optimizations, even if the immediate speedup isn't always dramatic. It's about optimizing a fundamental building block.
Okay, that makes sense. So we've really dug into FlashNorm here, seeing how these uh, quite clever mathematical rearrangements, reordering steps, fusing things together, how they can make these core normalization layers potentially more efficient inside LLMs.
It really is fascinating, isn't it, how tweaking these fundamental components can ripple outwards, affecting not just speed, but maybe even how we think about designing the architecture of these huge, complex models. And like you said, they're already thinking about next steps, getting this into common frameworks people use.
Absolutely. It definitely makes you appreciate the hidden complexity and the potential for optimization that still exists even in these foundational layers we often take for granted.
Totally.
So for you listening, what's the key message here?
I think it highlights that progress in making LLMs better and faster isn't always going to come from some brand new revolutionary algorithm. Sometimes, maybe often, it comes from looking really closely at the operations we already use and finding smarter ways to structure those computations, making them simpler, more parallel, better suited to the hardware we have.
Yeah, that's a great point. Which leaves us with a final thought, perhaps. As we keep pushing for faster, leaner, more efficient LLMs, how much of that future progress will stem from completely new ideas versus the meticulous refinement and optimization of the building blocks we've relied on for years?
Something to ponder.
Definitely. Thanks for joining us for this deep dive. We hope you'll keep exploring these fascinating topics.